Welcome to this session of Shadow the Scientist, Astronomy Night with the C3VO team, hunting giants at the edge of the universe. My name is Jamika Marshall. I'm your session host and the Shadow the Scientist Programs Manager. Now, Shadow the Scientist is an initiative that's brought to you by an incredible team of people at the University of California, Santa Cruz, and we are funded through a generous grant from the Heising Simons Foundation. Now, in this session, you are in for a treat. Not only do you have a host of amazing science presenters here, but you will be participating in the very first Shadow the Scientist session featuring this brand new Prime Focus Spectrograph that's mounted on the Subaru telescope. Now, in these observations, the team is planning to use this incredibly powerful spectrograph, and it has a new Hawaiian name, and we'll learn more about that later in the session. But they're going to be using this Prime Focus Spectrograph to study a large sample of galaxies and some of the largest structures formed in the early universe, approximately 10 to 12.5 billion years ago, when the universe was only 10 to 20% of its current age. Now, the primary goal of these observations is, of course, cosmic cartography, but the team will also examine how frequently galaxy interactions and mergers occur as galaxies fall into these immense structures, as well as the effect of this kind of activity on member galaxies as they grow and develop. Now, we have a huge group of amazing science hosts. So I will start with Dr. Brian Lemaux. Brian, welcome.
Aloha, everybody. I'm Brian Lemaux. I'm a staff scientist at the Gemini Observatory. In fact, I'm based in Hilo. Gemini North is a different telescope than Subaru. We're a little bit east, about the same size, both about 8-meter diameter mirrors. I usually observe with Gemini. My main job, my day job, my night job is to support the Gemini telescope, but I'm here doing research or hoping to do research tonight with the Subaru telescope. So Mauna Kea Observatories and astronomy in general is a very community-driven endeavor. And so astronomers use all different types of telescopes for all different types of capabilities. So I'll pass over to Kumiko to introduce the Subaru telescope, and then we'll maybe do quick introductions of everybody.
Can I share the screen?
Of course.
Good evening. My name is Kumiko Usuda-Sato. I'm a Japanese astronomer, and I'm doing public outreach. My job is a public outreach specialist working at Subaru telescope. Let me introduce very brief introduction of Subaru telescope and our observatory, National Astronomical Observatory of Japan. So Subaru is one branch of NAOJ, and its headquarters is in Tokyo, Japan. And Subaru has some official social media accounts. Please, sometimes both in Japanese and English, sometimes in English. Please follow us. X, Facebook, Instagram, and YouTube. Okay, so this is a picture of Mauna Kea observatories. You see, many telescopes, and Brian Gemini nose telescopes over here. And our Subaru telescope is this one, very unique, cylindrical silver dome. So on Mauna Kea, Subaru 2K telescope, Gemini 8 to 10 meter world-class telescope. And you may know, we had two telescopes, one of sub-meter telescope, one is University of Hawaii Education Telescope. They are already decommissioned, so there's no longer available. Now, 11 telescopes on Mauna Kea are working. So we are on the big island of Hawaii. This is a very big island, and Mauna Kea is over here. And we are not here. Telescope is on Mauna Kea, and we are from Hilo, or sea level. So we are from a remote observation room. We observe with the Subaru telescope on Mauna Kea. Actually, Subaru telescope has 3 observational rooms. One is, of course, on Mauna Kea, and number 2, where we are here, Hilo, on the Big Island. And number 3, so we are Japanese telescope, so the third observation room is in Tokyo at NAOJ headquarters. So we connected with Zoom and we communicate Mauna Kea, Hilo, and Tokyo or other places and do observations. Today, nobody from Mitaka side, but many people join observation from many places in the world. And this is a picture of Subaru telescope. The strong point of Subaru telescope is Subaru uses 4 foresight. So this is a telescope, Subaru telescope model about 100 times smaller than the actual size.
You may want to show the
camera. Oh, right. This one, maybe it's too small. That's okay. You see the screen. So the Subaru telescope can mount the instrument at the top of the telescope over here. We call this focus prime focus. And also we use the bottom of Cassegrain focus and 2 Nasmyth foresight. And for example, Keck uses Cassegrain focus and Nasmyth focus. And Gemini uses only Cassegrain focus, but Subaru can uses prime focus using the wide field of view instrument. For example, HSC, hypersphere cam, can cover 9 full moons, and tonight's instrument we use ʻŌnohiʻula PFS. Actually, ʻŌnohiʻula PFS is a very complicated instrument. It consists of prime focus instrument and spectrograph system and the meteorology camera and Cassegrain focus and fiber. Later, our colleague will explain more details. So today's instrument is ʻŌnohiʻula PFS. PFS means prime focus spectrograph. This picture is M31 under the galaxy captured by HSC, hypersphere cam with Subaru telescope. It can cover 9 full moons and using the same field of view, using ʻŌnohiʻula prime focus spectrograph, can obtain approximately 2,400 spectra simultaneously. It's very powerful instrument. I stop my presentation and give back to Brian. Thank you.
So just to clarify, so in a single pointing, so you have these 2 behemoths of instruments. You have Hyperis Prime Cam, yes, which is an imager, so just takes pictures, right, in different colors. And that's the picture of the, let's say, nearby galaxy. There is HSC, single pointing of HSC, several different colors.
Yeah.
And then the next step in a lot of astronomical endeavors is then, okay, you get the colors, but it's just kind of bulk colors, and then you push a little bit further to get the spectroscopy, so to get the full wavelength of rich and more detailed color
information from each stars and galaxies.
And so I guess we'll cover this more later when we talk about the power of ʻŌnohiʻula PFS.
Yeah.
But when I was growing up in astronomy, maybe if you were really, really lucky, you would get 100 sources at once to get a spectra. And PFS, more than an order of magnitude increase on that number of spectra at once. So, and now by far it's the most powerful spectrograph.
Right. Thank you so much, Brian. So Subaru has many instruments. For example, other instruments like MOAX, infrared focus in optical wavelengths, and they can get multiple spectra, rainbow, from stars and galaxy. But it's up to 50 spectra at one time. But ʻŌnohiʻula PFS can get 2,400 spectra at one time. It's many spectra, many rainbows from stars and the galaxies.
And it's not only the number of objects that you can target, but one other virtue of it is the large wavelength. So it goes almost to the atmospheric cutoff in the blue, so bluer than humans can see, all the way to well into the near infrared past human range of vision.
and beyond red, we see, we can observe near infrared too.
So you get tons of objects, you get very fine information on the colors, and you get a huge baseline in wavelength or color. So it's pretty much anything you could ever dream of as a as a researcher, especially when you're doing galaxy evolution studies and galaxy surveys. So of course it's super powerful for a lot of different reasons, but for our purposes, it's extremely efficient for galaxy surveys, especially the distances we're looking at. Okay, well, thank you so much.
Oh, thank you.
So maybe we could just do quick introductions besides myself and Kumiko and Jamika. So maybe I can pass to the rest of our team, and then the rest of the Subaru staff to feel comfortable talking. So Finn is actually the principal investigator of this, so I'm just along for the ride. Finn, do you want to introduce yourself?
Yeah, hey, camera's here. Hey, I'm Finn Giddings. I'm a fourth year, I guess, graduate student, current PhD student at the University of Hawaii Institute for Astronomy. I work with Brian and Roy and some of the other members of the C3VO team. I've been studying galaxies for a couple years now.
You're actually on a different island.
Yeah, actually, yeah. So I normally am on Oahu. I guess I live in Honolulu, but I came over obviously for these observations to be at the base facility to get to use all the fancy screens and stuff. I think also too, I saw some folks are in the chat from Memphis. I actually spent 4 years in Memphis. I went to Rhodes College for undergrad, so welcome. Hope maybe you guys know where that is. Yeah.
Sweet. So we also from our research team, we have Roy Gal on the call. Roy, do you want to introduce yourself?
Yes, aloha everyone. My name is Roy Gal. I'm a professor at the Institute for Astronomy at the University of Hawaii. I'm one of Finn's thesis advisors, and I've been working with this research group with Brian since he was a wee lad as a graduate student, something like 25 years, 20 years,
Roy, you don't need to say it.
30 years ago, whatever.
40 years ago.
I do research. I've been doing research on galaxy clusters and sky surveys and galaxy evolution for a long time. And I also run our public outreach activities at the Institute for Astronomy here. And I'll be talking about spectroscopy later on to introduce how that works and what we're trying to do.
Great, thanks, Roy. And then we have Joel, the other member of our research team that's joining us. Joel, you want to introduce yourself?
Yeah. Hi, I'm Joel. I am currently an undergraduate student, I was an undergraduate student at the College of Charleston. I'm in my second round of applications for grad schools right now. It's a little rough, but that's okay. But I've been working on a separate project from Finn, so I'm here to just along for the ride for all the observations, which, I mean, it's always fun. So I'm currently working on a survey that we took back in 2022 from a different instrument on Subaru called SWIMS. It's now no longer in use. I believe it moved to Japan, if I'm not mistaken. But we took data from our observations there, along with data from I believe it was an ongoing survey done in Chile by Paranal, right? The VUDS instrument. And so right now my goal is to try, I believe, did you already go over spectra and kind of?
No, we haven't done any science yet,
Okay.
so we're still warming up to science. But yeah, so you've used Subaru instruments in conjunction with other telescopes to look at basically the same structure that we're partially looking at this evening, and we're hoping to look at this evening, just from a different perspective, right?
Yes. It's all about Hyperion.
Thank you, Joel.
Of course.
Are there other people in the room that would like to introduce themselves? Akira, do you mind introducing yourself?
Introduction?
Yeah, that would be great. Yeah, if you don't mind.
My name is Akira Rai, so I'm a supporter soon PFS. Yeah, so yeah. Yes.
Aloha, everybody. I'm Shweta. So just like Arai-san, I'm also a support astronomer. So my name is Shweta. And I have just recently joined the PFS team, and I'm very happy to be a part of it and support astronomer.
No, terrain.
Yeah, Yeah, tonight's official training for you for the instrument.
My official night of training on science observation.
Okay.
Keeping fingers crossed.
Okay.
For weather.
Yeah. Yeah.
And you have your trainers surrounding you. They see. So. Yuki, would you introduce yourself?
My name is Yuki Moritani. I'm one of the instrument group of I think I will introduce some other.
Yeah, so we have a lot of kind of talks lined up, and Yuki is going to give us a behind the scenes look at the development of the Prime Focus Spectrograph. Then Vera?
Yes. Hi, everyone. I'm Vera Maria Paseka. I'm from Austria. I'm also a EFS support astronomer, and I work here since 2 years.
So you know we are very international team. So Subaru is Japanese telescope on Mauna Kea, Hawaii, USA, and we are Japanese. Please introduce your nationality.
Yeah, by the way, I'm from Nepal.
Yeah, Nepal, and Yuki-san from Japan, and Vera is from
Austria.
Austria. We are international team.
Yeah, and that's not uncommon among all the Mauna Kea observatories. Gemini is funded by 6 different member nations, and we have 20 different nations represented among the staff there. So yeah, this is truly an international endeavor. And then we do have the summit crew here. I was wondering if anybody wanted to introduce themselves. I don't know, Summit, if you can hear us.
Sorry, what was that?
Oh, I was just wondering if you wanted to introduce yourself. The participants for this outreach event can't see you, but they can definitely hear you.
Okay. My name is Jonathan. I'm a telescope operator here at Subaru. I've been working here about 4 or 5 years, and I work week-long shifts at the summit here, and do everything from telescope safety checks to some instrument operation, telescope operation.
So you're the guy that's going to decide whether or not we open tonight.
Yeah. That'll be the weather, but
that'll be the weather, sure.
Yeah.
You'll be monitoring. Yeah, so Jonathan's on near the summit of Mauna Kea right now at the actual Subaru facility at the flanking building right next to the telescope. So we're all comfortably situated in Hilo, and Jonathan has to deal with the cold and wind and other things that are going on up there. Okay.
Michael, if you wanted to say something.
Yeah, I think Jonathan was the one who wanted to say something. Thanks, Jonathan.
Yeah.
So as we kind of alluded to, the weather's not great tonight, and in fact, so yesterday,
Some stuff that the humidity is very high.
yes, what is it right now? So 98% relative humidity, at least the Gemini. So we are currently closed. Yesterday, Kilauea, the volcano to the southeast, decided to go off. So we actually went up to the summit yesterday for a tour with Vera. Vera kindly took us up, and we got to see the plume of ash. And so Hilo was covered in ash yesterday, thin layer, but yeah, Pele's hair and ash. So that was one issue. And then we had not uncoincidentally, we had a storm come in, shifted around the wind pattern. And so we are currently waiting out the storm. I see some sky behind the humidity and the clouds. So I'll just share my screen really quick.
You know what's funny about that, Brian?
What's that?
That's our 3rd time in a row.
Third time in a row
of eruptions happening like the day before day of observations.
Yeah, so we were on Keck on December 23rd also, when in the middle of the night Kilauea went off. So yeah, it's not an uncommon occurrence nowadays. It's about every 2 to 3 weeks. So these are super light sensitive cameras from Gemini on the outside of our summit facility, looking the 4 cardinal directions and then up. You can see actually that there are some stars through the clouds. But unfortunately, the number right now that we have to pay attention to is this one right here. So the humidity is near 100%. But did you guys look at the particulate counts today? Are they particularly bad? Because the high humidity with the SO2 is a very bad combination. And I know you guys lowered the humidity threshold, right, for when Kilauea is off-gassing. And even after the main eruption event, it's sometimes pretty bad. But yeah, so we're hoping, hope against hope, that we open this evening. We've been blessed with incredible weather, the other runs that we've had. And so we're now on the other side of the karma coin.
Yeah.
But we still have some hope. And so we're just going to talk a little bit about some of the physics behind what.
Wait a second.
Yeah.
We received one question.
Oh, sure.
Please ask about
Yeah.
humidity.
Okay. Yeah, so we were planning on talking about some of the physics behind the observations. We were going to talk about some of the science. We'll talk about the instrument. We'll talk about the naming of the instrument. So these are all things that we'll do. And then if we miraculously open, then we get to see some photons as well. So there was a question in the chat about humidity within the dome. Is there a safety threshold within the dome? Is it 90% just outside the dome, or how tight is the dome against humidity? I could answer for Gemini, but I don't want to answer for Subaru. So if it's inside the dome, is it relatively well controlled with ventilation and everything? Do you guys have an inside the dome and outside the dome?
Yeah, that's maybe something John can answer.
Okay.
Yeah.
John, did you hear the question? Are you in the room? So the question was, is there a differential between the relative humidity as measured in the dome versus outside?
Yeah.
Yeah, it's slightly less right now, but we're still at our
Yeah, right. Yeah. I'm not expecting that to change too much. Yeah. You guys, so you have monitors actually inside and outside the dome?
So this is the
Okay.
answer.
So this is the outside inside. Yeah. So there's a little bit of a lag time. It's probably not airtight, but a little bit of a lag time. So try to keep the humidity in the dome as low as possible. Humidity is not good for optics or instruments. There's also potential for precipitation this evening. There's also potential for ice. There's also potential for lightning strikes. So we got the kind of full Mauna Kea experience lined up tonight. Full closed dome experience, let's say. Okay, so maybe I'll pass over to Roy to talk a little bit about spectroscopy and why you'd ever want to do it and what it's good for. So I will stop sharing and I will pass to Roy.
All right, thanks, Brian. So I'm going to give our viewers who may come from very different scientific backgrounds or not even science backgrounds. So I'm going to start at the beginning and try to build up to the underlying physics of what of how this instrument works and what spectroscopy is about. So if it's too basic for you, sorry. And if you have questions about it, please ask in the chat. So just give me 1 second to get my keynote started here. Okay, so I'm going to tell you broadly how we learn about the universe from light and what spectroscopy is, and what are some of the things that we can learn about an object from the light that it emits. And like Brian said, many of you are used to seeing pretty pictures. You saw the pretty picture of the Andromeda Galaxy taken by Hypersuprime Cam. But most of our scientific knowledge of the universe comes from actually breaking up the light into its colors and decoding that for clues as to what things are made of and other properties of objects. And I'm at the Institute for Astronomy. We do a lot of public outreach. We have social media as well, so you can find us at UHIFA on Instagram and Facebook. So what we know about spectroscopy actually started hundreds of years ago with Isaac Newton, who was the father of many of the fields of modern physics. And he did a simple experiment where he passed light through a prism and saw that it made the colors of the rainbow. Obviously, people saw rainbows before, but they didn't understand how they formed. And he did an experiment where then he said, okay, well, I see all these different colors. What happens if I try to pass a specific color through a prism and you still get that color? So what he learned was that color is some kind of inherent property of light. It may sound strange to us, but before then, people thought that color came from our eyes, that we didn't actually, light wasn't received by our eyes as the sensors or detectors, but somehow we shot out beams of stuff to objects and it would bounce back and give us information. We did not understand all these things that we take for granted about how light works. So his basic experiment was he took a darkened room, made a pinhole in a darkened window, sunlight would come in, pass through a glass prism, and it broke up into the colors of light. And that rainbow is a visible form of what we call a spectrum. And when we have a tool that records a spectrum, that's a spectrograph. So that's why it's the Prime Focus Spectrograph. It's a tool that breaks up the light into its constituent colors and records it. And it sits at the prime focus of the telescope, as Kumiko said. And so that's why it's the prime focus spectrograph. So when we take a spectrum, we might see that as a rainbow, as in the top here. And you'll notice that this rainbow has some odd dark lines in it, and I'll explain where those come from later. But as scientists, we don't just look at this, we actually record in a graph how much light we get as a function of the color of the light. And that color I'll talk about, we measure usually as a wavelength. So if I translate this rainbow with these black lines into a plot, this is what we normally talk about as a spectrum. We see that there's a lot of yellow and green and blue light. There's very little purple light. There's less red light. And there are specific colors that are missing where the light isn't getting to us. And this is the kind of spectrum that we would get from our spectrograph and then try to decode what this tells us. So as astronomers are always being scientists are always being quantitative. We don't just look and go, ooh, that's pretty. We actually have to make measurements with numbers. And here's an example of a very high resolution spectrum of the sun. And you read this like a book, starting at the top left corner and going over to the top right corner, and then you go to the next line. And if you were to make this into one long strip, right, you could imagine cutting each strip, attaching it to the one before it. And you can see all of these amazing features in this spectrum. So many of these dark lines. Some are stronger, some are weaker, some are wider, some are narrower, some are really fuzzy, some are really well defined. And by looking at the patterns of these lines, they're like fingerprints that tell us a lot about what's in the object, how hot the object is, what kind of interactions are going on, all kinds of things. So just like a police detective might grab a bunch of fingerprints off a doorknob and try to figure out who they belong to, we see these fingerprints imprinted in the spectrum of a star or a galaxy, and we try to figure out where they come from. And that was a visible light spectrum. The rainbows that we see in the sky here in Hawaii all the time are visible light that we see with our eyes, but there are many other colors of light that we are totally not sensitive to. Infrared is an example of that. You feel that as warmth on your skin, and night vision cameras have sensors in them, and cats have sensors in their eyes that can see infrared light, but we can't. There's X-ray light, there is ultraviolet light, there's gamma rays, radio waves. Those are all forms of light. They're all part of the electromagnetic spectrum, which extends way beyond what humans can perceive, but which objects in space give off colors, all wavelengths of light. And so we actually use many different kinds of telescopes and many different kinds of tools to study that. And as Kumiko and Brian said, this spectrograph is really amazing because it actually takes the light and sends part of it to a camera that's sensitive to visible light, and another part of the light to a different camera that's sensitive to infrared light that we can't see with our eyes, and records it at the same time. So that's very unusual. Usually you have either a visible light or an infrared light instrument, and this kind of does double duty, which is very, very powerful. When we talk about light, it's a wave of electromagnetism. And like waves that are in water that we're very familiar with here in Hawaii, you can measure what's the distance between one peak and the other peak, and that's the wavelength of light. And that's what we often, as optical astronomers, visible light astronomers, we use that wavelength to characterize the color of light that we talk about. But you can also measure how fast those waves pass you by if you're standing on the beach and you count, okay, a wave hit me and 5 minutes later, another wave hit me, then that's 12 waves per hour, and that would be the frequency. And so we measure the frequency of light in hertz, Hertz. That's uh, the frequency of light. So you might hear that term when we talk about light. And for waves, there's an equation where if you multiply together the wavelength of a wave and its frequency, you get the speed of that wave. Well, for light, that speed in a vacuum is always the speed of light. And what that means is if the wavelength gets higher, the frequency has to get lower because you have to multiply them together. You always have to get the same number. If wavelength is 10 and frequency is 1, then you change that, then the wavelength is 1 and the frequency has to be 10. They always have to multiply together to add up to the same, to multiply to the same number, which is the speed of light. So when astronomers talk about colors, very specifically, we might be talking about a wavelength or frequency of light. We attach a number to that color. So yes, we might say red. We have red filters, but when we do analysis, we talk about specific colors as wave frequencies. And so we're back to our spectrum, which is how much light, the intensity of light, as a function of the different wavelengths of light. And so that's what we measure with these tools. And we can think about the broad range of the electromagnetic spectrum and the kinds of objects that give off those kinds of light. And we start with very short wavelengths, which have very high frequencies because you multiply the two together, you get the speed of light. And those are gamma rays. That's what turned Dr. Banner into the Hulk. They're super high energy. And they're actually really bad for us. They have so much energy that if you're hit by gamma ray light, it fries your cells. That's bad, right? That's why he mutated. On the opposite end, you have radio waves. That's what my cell phone gives off, among other things. And those are very low energy with long wavelengths that are measured in meters or centimeters. And then we have right here in the middle, this teeny, teeny, tiny portion is visible light that we're sensitive to as humans. That's what our atmosphere lets through. Um, and the wavelengths of that light are like a millionth, or 10 to the minus 6. So they're about 1 millionth of a meter. Very, very tiny wavelengths. Okay. And so we're recording light of those wavelengths. And here's an example of why we look at the universe at different wavelengths. This is looking at the Milky Way galaxy at different wavelengths of light. And what we normally see with our eyes down here in the optical, and you can see these dark lanes or dust that block the light from getting to us. But if you look at other wavelengths, light passes, like the infrared light passes through that dust, and that dust actually glows. And you can see some things that only show up in X-rays that we might not see in visible light. So we're always studying the universe in many different colors of light. Okay. So let's think about what light can teach us. So light and matter interact in four basic ways. Okay, and the terms, these are our science terms: emission, absorption, transmission, and reflection or scattering. So we'll go through these very fast. Okay. Emission, to emit something, means to give off light. So a light bulb gives off light. You give off light. If I look at you with an infrared camera, you are glowing in infrared light. Most things that are warm, like temperatures that we're used to, plants, Earth, us, we glow at infrared wavelengths. Stars, planets, galaxies, they all give off light. But those things also absorb light. If I'm outside and I'm in the sun, I warm up, my skin gets hot. I'm absorbing some of that sunlight. Black pavement, right, absorbs lots of different colors of light. That's why it's black. That makes it super hot. You put food in your microwave oven, some of the light is absorbed by the water in there, and it makes the water molecules jiggle, and that's how you heat up your food. You can also transmit light, like a window pane, or an X-ray image, right? X-rays pass through your skin and bounce off of bone, and that's how you get an X-ray image. And finally, light can bounce off of stuff like a mirror, like a telescope mirror. I should have put in a Subaru picture here, but this is a Keck telescope, one of the other telescopes on Mauna Kea. And my shirt, it's bouncing light off. It's getting different colors of light hitting it, but only the colors that make it look tan to our eyes are bouncing off and the rest is being absorbed. And you know that if you wear a black shirt, it absorbs lots of colors of light, and a white shirt bounces more of it back. And when we look at the world around us, all of these things are happening all of the time. And it's actually really interesting to look at the world through this scientific lens and ask, how am I perceiving what's going on? And that's part of being a scientist, of being curious about like, oh, what's going on? So if you're a person standing in a room and you see a red chair, why is that chair red? Well, the light bulb and the sunlight coming through the windows aren't red. It includes red light. So the red light that's coming from those sources is bouncing off the chair, but the other colors are being absorbed. And if you see that chair in a mirror, that light from the sun and the light bulb is hitting the chair and bouncing off and hitting the mirror and bouncing off and entering your eyes. It's amazing what's happening. So that's how we perceive things and how we can learn about them. And when we look at a spectrum, when we break up those colors of light, there's basically three kinds of spectra that an object can give off. And often it's a combination of these that we're getting. If you have something that's got a temperature and is dense, like a charcoal briquette, like your body, like a planet, part of the spectrum that it gives off is a continuous spectrum, or what we call a thermal spectrum. Something dense with a temperature gives off that spectrum. And that's the rainbow that you see in the sky that looks like this. You're seeing the sunlight. The sun is hot and dense, and it gives off all colors of light. And when you spread that out, you get this beautiful continuous rainbow. But if you have a cloud of gas, the interactions that happen in there are different, and you don't see all the colors. You get a very specific pattern of colors that depends on what that gas is made out of. Is it hydrogen? Is it water? Is it oxygen? Is it neon? All those give off different patterns. And if you were to instead take the sun or a light bulb or whatever and put a cloud of gas in front of it, you would see this continuous rainbow with some of the colors missing that are absorbed by that same gas. And we can learn from these spectra all kinds of things about objects. And this is super important for astronomers because we cannot go up in space and scoop a piece of a star and put it in our lab. We cannot go travel back 80% the age of the universe and touch that galaxy like we can for plants or DNA or paint or whatever we might want to study in a lab. So we have to learn from the light that gets to us. So one thing we can learn immediately from an object, especially if it gives off a continuous thermal spectrum, is its temperature. And the hotter an object it is, the more brightly it glows, but also the different amounts of light it gives off at different wavelengths changes. A hot object gives off lots of ultraviolet light and very little infrared light. A cooler object like us, we're like this temperature, we give off no visible light, no ultraviolet light, but we give off mostly infrared light. So if I can take a spectrum of an object and make this plot, I can immediately convert that to the temperature of the object without having to go and stick a thermometer in the sun, in which case I would be vaporized and I wouldn't be able to tell anyone about it. And a fun fact, if two objects that are hot and dense have the same color, they must have the same temperature. So the sun and this glowing incandescent light bulb have the same temperature, which is crazy. That wire in that light bulb is thousands of degrees hot, which is why it burns your hand even if the glass is around it. And that may seem insane. That's 10 times as hot as your oven, but that's the truth. Okay. I'm not going to go into atomic physics, but very basically, atoms have different levels of energy for the electrons in them. And when those electrons jump up and down between levels, they can emit light. But because those levels are like the rungs in a ladder, the light that's given off has to correspond to specific energies, and specific energy of light corresponds to a specific wavelength. And each different kind of element, each different kind of molecule has a different pattern of rungs of the ladder, which means they each give off different patterns of colors of light. So here's an example of colors of light given off by different atoms: hydrogen, helium, oxygen, I believe, and neon. And you can see they're completely different. Your eye will perceive actually this spectrum. If you combine this purple, blue, and red, it looks pink to your eye until you spread out the light and realize there is no such thing as pink. Pink is a construct of your brain. This color what you perceive as pink is a mixture of colors that your brain interprets as pink. But if I break up this particular pink light, I get purple, light blue, and red. And so when we put spectroscopy together, if I take a spectrum of an object, I might see its thermal emission. I might see absorption from the atmosphere, gases along the way. I might see reflected thermal emission from something else. And we have to interpret all of that, and that's how we're going to use this instrument to learn about galaxies. And their spectra are very complicated because galaxies are made up of millions or billions of different stars. They have gas. They have all kinds of dust. They might have a black hole that's active. They have all kinds of things that are happening in there that we have to disentangle. And this instrument is going to help us do that. And Finn is going to tell you about how we apply these ideas of spectroscopy to the science that he's trying to do and that our team is trying to do across the universe.
Thanks, Roy. That was super informative. Ben, do you want to show us what we're hopefully looking for?
Yeah. I can follow up on that. I'm going to start probably really big picture and then hopefully get back into, I guess, towards the end of a few different things, get kind of back to the spectra part of it. And some of the things we're trying to measure, I'll probably focus on maybe one key parameter we're trying to measure for a lot of our sources. But
perfect.
Let me share my screen. Hopefully everyone can see this. So I think first thing I wanted to mention was I think we've maybe thrown around this C3VO term a couple times, and I just wanted to quickly touch on what this is, what this means. Here's a picture of kind of the team, and so this, what this stands for, and what you find in astronomy is people really love making fun acronyms for things, and so the fun acronym we use is the Charting Cluster Construction with VUDS and ORELSE, so 3 C's, C3, and a V and an O, which are also other acronyms. We have acronyms within acronyms.
The best astronomy surveys have nested acronyms, and in fact, we're at 3 acronyms nested.
Yeah, which is pretty impressive as far as the astronomy acronyms go. So
because VUDS is also has an acronym.
That is true.
Yeah.
So that's kind of what the group and I guess people that me and Joel and Brian and Roy all kind of work together with. And so briefly, I'm going to use an analogy that I've heard Roy use many times that I think might help context kind of what we're starting. First is just look at this image of the Earth at night. I mean, one thing you can kind of notice is there are collections of where there's a lot of light and there's places where there's not a lot of light, right? And so that's kind of tracking kind of our cities versus our towns versus our more rural areas. And so there are places on the Earth where a lot more people live versus where not a lot of people live, right? The density of New York and Tokyo was a little bit different, or the amount of people living there is different from maybe Rolla, Missouri, or Hilo, Hawaii, right? And so there's a wide gradient of, tons of people living in really tight proximity to maybe some people living more out on their own, I guess. And so,
not to derail you here, but a fun question to also ask is, does light trace population?
That is a great question.
Because anytime you make these types of analogies,
yes, that's true.
I mean, you can go even further because we're looking for galaxies to trace overdensities, right? But it may be that galaxies don't trace overdensities.
It may not be the perfect tracer, right? There are definitely other tracers that people use aside from galaxies, like I guess looking for some sort of large gas reservoir or something to maybe try to trace underlying bits of our universe aside from the galaxies. We use the galaxies primarily, but
and like for an example, in Hilo, we have light ordinances all over the Big Island, and so we try to protect the dark skies, and so it may be that how light traces population here is not the same
as
in
how
Tokyo, New York.
Yeah, it's true.
So yeah, just wanted to add that.
No, appreciate that. So I guess with all of this, there are always lots of caveats, and I'm trying to give a 1-to-1 as much as I can, but there's always something going on.
So we're going for the lights.
Yeah, we're going for the lights, yeah. And so to further highlight this again, if we maybe zoom in on New York, you can see Manhattan and Long Island. Tons of people living here, and maybe as you move out, I think this is probably Rhode Island, Connecticut. I've never been here actually, but maybe less people up there. And so just as people tend to cluster into cities, we find that in our universe, galaxies tend to cluster kind of in this structure called the cosmic web. And I won't go too much maybe into details of this, but this is kind of the underlying dark matter distribution of our universe, and where this kind of spider web of dark matter crosses, we have these things they're called the nodes, and oftentimes at these nodes you find overdensities or more galaxies, kind of like a city of galaxies. Though not all of these overdensities, like Brian mentioned, are populated with tons of galaxies. Many of them are, or at least that's how we've been able to study them.
Yeah. But just to clarify here again, that this map that you're showing is of dark matter.
This is
right?
of dark matter.
So this is the matter dominant form.
Yeah.
But it may be that galaxies trace this density structure in a different way than the dark matter does here.
Exactly. Yeah.
Generally, there's a one-to-one correspondence ish, but there's definitely caveats associated with that.
For sure. So we try to, as best we can, adjust for those caveats, adjust for those biases and things, but not always perfect.
And we can't directly observe dark matter either, right? So we can see its effects through gravitational lensing or through the movement of galaxies, but we can't directly image it or get spectroscopy of it. So this is why we go for the galaxies.
Exactly, yeah. So all the light processes that Roy was talking about, whether they're emission or absorption or all these different parts of light that you can break down and measure with something like BFS, you can't do that for the dark matter. And so we have to do that for the galaxies or other things that are made of matter that we can find, right? Yeah. And so in the local universe, again, something might look like this. And so maybe if you look nearby us in the universe, you might see something more like this. What we try to do is we try to push further into the universe, or farther back in time, where that same structure might look something like this. And so I guess this is maybe a city of galaxies that is in the process of forming, and so there are slowly more and more galaxies coming in together to kind of make this city of galaxies.
So I'll just pause for a second. So there was a question in the chat by Bonnie. Will having the spectrograph affect the type of research that will be chosen for telescope time? So I guess, is the research catered to the capabilities of a spectrograph? So why are we on Subaru tonight, for example, rather than Gemini or Keck or Cerro Paranal or Magellan or something?
Yeah, so I mean, it really depends on, and I think I will touch on this, but just to give a I guess a brief answer. I guess if there's a particular question you want to know, there's a particular thing you want to ask and learn about space. Maybe it's how galaxies are clustered. Maybe it's why is there an exoplanet around this star? Those sorts of things. Depending on what you're trying to learn, you need to cater to what instruments or what fancy things you can point at the sky a particular telescope has, and that I guess dictates what telescope you might try to use or what questions you might try to ask, because maybe you have some really cool, interesting question, but if there's no instrument or no telescope that can get you light that helps you answer that question, unfortunately, you can't answer that until somebody makes a new fancy instrument that then can answer the question. If that is helpful, I think.
Yeah, so that, like, for example, Gemini has two instruments that are fairly high resolution spectrographs, but a single target.
Yeah.
So they're hundreds of times better resolution. So the gradations of light, you can get much more finely, but you can only do it for a single object. So if you're really interested in planetary atmosphere or stellar atmosphere or stellar kinematics, then you might go for that type of spectrograph. But if you're interested in getting as much data as possible on thousands of galaxies to map out the universe, probably Prime Focus Spectrograph is the one you want to choose.
Yes, a single object spectrometer might not be, or spectrograph might not be the best choice for that. Yeah.
It takes a little while.
It would take you, I guess, if you did maybe one galaxy a night, it'd take you 2,400 nights. And so, how many years is that? 8 years?
Yeah, so the time allocation committee would
not like
frown on that.
Yeah. And that's assuming you're going to be able to open the dome every night. There's no moon, all these other aspects that we're dealing with tonight too.
Mm-hmm.
So, with establishing C3VO is trying to look at, I guess, cities of galaxies maybe as they kind of form in our earlier distant universe. I guess just to kind of really hone in on what are the two, I guess there's a few other, there's a lot of different targets that go into I guess when we're planning these masks and trying to set up, okay, what are all the different fibers we're going to assign to different galaxies? I think the two kind of main drivers I'm going to maybe focus on are, okay, mapping that underlying structure of galaxies in the early universe. And so really understanding where these overdensities of galaxies are, trying to confirm them, those sorts of things, trying to make sure, okay, we see all these galaxies here, are they actually all there? That kind of thing, kind of a mapping of sorts. Our cartography, I think, is the word Jamika used earlier. And then another thing that I'm in particularly very interested in is the identification of future galaxy mergers, which I'll get into. But essentially, what you can do is if you find two galaxies that are maybe in a pair, or galaxies that have a close companion, if you find two galaxies that are really close to each other in the universe, they're probably going to merge and crash into each other in the near future. And so trying to find those systems is something that I'm particularly interested in conjunction with maybe these densities of galaxies where you might have all these different galaxies flying around each other, crashing into each other, and doing these sorts of things.
So a couple of questions for you, Finn.
No, yeah, of course.
Number one, why do you need spectroscopy for cosmic cartography? Well, why do you need to measure the spectra of galaxies to determine their location?
Yeah. So I actually have a slide, maybe about that.
Okay.
That's if I'm allowed to.
Yeah. Perfect. Yeah.
Okay.
Okay. Yeah. Is it the next slide?
It's like two more slides.
Okay.
I was gonna break these down a little bit and then talk about how I guess there's a common thing you can get that can help you answer both these questions.
Okay. All right. I'll stop asking.
No. I think
I'll do one more. So how faint are these galaxies? I mean, the Subaru telescope is an enormous telescope. It's an 8.2 meter aperture primary mirror. So the diameter is 8.2 meters. Why do you need something this big for these types of galaxies?
Yeah, that's a great question. So maybe if you look up into the night sky, maybe you're somewhere on the Earth where hopefully there's not a lot of clouds. Maybe you can see some stars, right? You might look up.
So not Gila.
Not Gila. If you're not currently in Gila, Hawaii, hopefully you can look up, or maybe too dense in the city, you might be able to look up in the night sky, and you're going to see some stars, right? And so what astronomers use is a thing called the magnitude system. I won't go too much into it, but a lot of those stars we might assign numbers of, this is first magnitude.
I prefer Jansky's.
Okay. Or maybe like a first magnitude through, second, third, fourth. And so kind of how this works is essentially things with low numbers, maybe a first magnitude star, second magnitude star, some of the brightest objects in the sky. If you've ever heard of the star Sirius, I think that is the brightest star in the night sky.
That's the Hawaiian name.
Is the Hawaiian name as well. Yeah. So if you look in the night sky, you're going to see all these stars. They're going to be these what we call single digit magnitudes.
So I think Sirius is -2.
Okay. Yeah. So they're all very, very bright objects, right? And so it's a log scale. Every step's was it 2.5 times. And so if you're using this,
so you change magnitude by 2.5. You change a factor of 10 in brightness.
Factor of 10 in brightness. Yeah, exactly. So factors of 10 in brightness, you're seeing maybe in a good spot, maybe you're seeing to 8th magnitude or so. Maybe very great vision. Maybe you're seeing
peripheral vision, great vision. You've been eating your carrots. Yeah.
The galaxies I'm mostly looking at, or we're mostly looking at, are 24th magnitude, right? And so if you take 2.5 magnitudes, 10 times 10 times 10 times 10 times 10 times 10, we're talking, millions, billions times fainter than what you can just look up in the night sky and see. And so you need not only a large telescope to collect all that light, you need to sit there and integrate and collect light for a long time to kind of stack it and slowly gather enough photons or enough of the spectra to be able to see anything.
Yeah.
It's kind of the way.
So somewhere around 10 million to 100 million times fainter than the human eye can see.
Yeah.
So this is why you need a huge telescope and you need a super powerful instrument and you need to integrate for a long time. So expose for a long time.
Yeah.
So it's not just click one
millisecond
and you see everything, but this is building up. I mean, the objects that we were planning on looking at tonight and still hoping to look at tonight, you've already observed a lot of them for 8 hours on Subaru. And still we need more integration time for the faintest ones, right?
Yeah. Yeah. So for the faintest sources, we're trying to go maybe 12, 16, 20 hours if we can get it, to really get as many photons as we can and see all the different parts of the spectrum we want to see to try to answer the science questions we're looking for.
Okay, I'll stop annoying you.
No. This has been helpful. This is adding lots of important context, I would say. And so I guess just to hit back.
Sorry.
No, yeah.
One more question. Can you go back to that last slide?
Of course.
So you have two different pictures here. What's the difference in scale between these two things?
Yeah, that is a great question. And so, I can give you answers in megaparsecs and kiloparsecs, but I realize for the audience that is probably not the most intuitive of units,
Okay.
perhaps.
So parsec is about 3.21 light years, I think.
Yeah.
Off the top of my head.
What was it? Kiloparsecs, what is it? 3 times 10 to the 20 something kilometers. It's 21 or 22, I think.
Yeah.
Something like that in kilometers.
3.086 times 10 to the 24 centimeters, I think, is a megaparsec. So really, really large scales. Yeah. So light takes millions, or let's say millions of years to cross from one side to another for a megaparsec scale.
Yeah. And so a lot of the time when
light travels fast.
Yeah, light travels very fast, as Roy established, I guess, when he was talking about the speed of light. But for kind of our galaxy pairs over here, we might oftentimes use kiloparsecs to kind of measure the separation or the distance between them. Whereas
thousands of light years.
Yeah, thousands of light years. Whereas when you're looking at a protocluster, you're looking in megaparsecs to tens of megaparsecs, right? And that's, what is that?
10,000 to 10,000
tens of thousands of light years, right? So light would take 10,000 light years to cross this. And so this is already a very big distance compared to what
this would be millions of light years, right? Yeah, but 1,000 to 10,000 times bigger than the galaxy scale there, right? Yeah. And comprised of hundreds of galaxies, right? Yeah.
So we're talking very, very large things in our universe.
Yeah. So the on the right there might be like the distance between the Milky Way and Andromeda, the closest major galaxy to us. But the scale on the left would be much more like the local supercluster like Laniakea, or like the local group, something along those sizes. So tens to hundreds to thousands of galaxies in size.
Yeah.
And space is mostly empty space, so this is very, very large. Okay, thanks.
No, that was.
It's very similar. Like the scale on the left is very similar to the scale that you showed on your previous slide, the dark matter only simulation, right? Yeah.
Speaking of that dark matter simulation, gonna go back to it real quick. Again, as we've kind of been talking through, there's this cosmic web, there's underlying dark matter structures, and we find that oftentimes, so these are just representative galaxies kind of populating this cluster system, and we find that these galaxies in dense environments are oftentimes different from those not in dense environments. Maybe they have different shapes, they have different colors, they're forming stars in a different way or at different rates. They have different amounts of existing stellar material, those sorts of things. And so a lot of what we want to study and understand is why the galaxies are different, what processes or what things are happening in these environments that make the galaxies different from the things that are not in dense environments. But even before you can answer that question of why they're different, you need to know, are they in the structure or they're not in the structure? And so that's a tricky thing, right? When you look up at the night sky, you see two stars. Which star is closer? How do you determine that? And that is a question that we'll come back around to after I do one quick thing, which is, again, galaxy mergers. The other thing that or I guess we were trying to look at tonight. When galaxies merge, you have different, I guess you can trigger different levels of star formation activity. So perhaps you're going to change how the gas and dust in the galaxies, you're going to form a lot of stars really quickly. You can funnel gas and dust into the black hole in the center of the galaxy, which will create an active galactic nuclei as that, I guess the black hole accretes material. That's something interesting to study. You're going to assemble more stellar mass by putting the two galaxies together. And so these violent events that take a billion years to happen are a very interesting aspect of galaxy evolution that people like to study. And whenever you do this, a lot of the times when you're trying to identify galaxy merge interactions, you're looking at the sky, okay, how do I know a galaxy is merging or undergone a merger, those sorts of things. You can either look at them in two ways. I like to think of, you can look at for close pairs or find two galaxies that are close together. That we know based on simulations that people have done, these will probably crash into each other in the near future. Whereas there are galaxies that are more active mergers where you can see the galaxies physically starting to crash into each other.
Is this a time lapse over like the course of your PhD of like the same system, or how did you get these pictures?
Yeah, so these are different snapshots of different, I guess, different galaxy mergers. And so they're showing a kind of a different stage. So you might start at 1 and the galaxies get closer and you go to 2 to 3 to 4 to 5 to 6. But the reason that these are all different systems is, again, this process takes a gigayear. It takes 1 billion years for these galaxies to get close to each other and slowly
So you haven't been in grad school for 1 billion years?
I have not. I hope to not be in grad school for 1 billion years. That would be a tough predicament.
Okay.
4 years. 4 years has already been a good amount of time. Hopefully by 1 billion we're out of here.
Okay, sounds good. See what Roy has to say about that.
Well, yeah. Hopefully Roy is on board with that as well. So yeah. So there are the close pairs. There are the active mergers. For my science, or what we're trying to do tonight is we're going to be looking more for these close pairs, and so we're trying to figure out, okay, are these galaxies actually close enough to each other to be, I guess, be merging? And one thing you might be asking yourself is like, okay, Finn keeps talking about, I want to know where these things are. I look up at the sky, I can see it's right there. Well, it's not exactly that simple. And I think for both our science cases, I try to put something together for this. The distance here is key. And so what we're trying to figure out is, okay, when you look at the night sky, how close or how far away something is, right? You know where it is. Oh, you can see it. It's that high up in the sky. It's that far over. But you can't tell how far it is in that third direction or away from you, essentially. And so maybe we're here at Subaru, and maybe the galaxy's here, maybe the galaxy's here, maybe the galaxy's here, right? Could be any of these locations. And so how do you tell where it is in that third direction? And so a lot of the time, what we're going to use to determine where the galaxy is, or what we're specifically measuring for a lot of these spectra, along with other parameters. But at first, we're going to be measuring something called a redshift. And so maybe to get into this, and this is where eventually it'll tie back into what Roy was talking. Maybe if we're here on Earth, you see these galaxies. I won't have the time probably tonight to go into this. The universe is expanding. By and large, every galaxy in the universe is moving away from you. And as the universe expands, the space between the galaxies grows. And as that light travels to you, it will become redder. So maybe light that is blue might start off, maybe blue, maybe like a royal blue might start there. And maybe it'll get redder and redder and turn into a nice crimson by the time it hits your eyes here on Earth or hits our telescope. And so to measure a redshift, kind of what we do is we look at, I guess we take the spectra, connecting finally to what Roy was talking about first, or maybe on the left here, we've got some sort of original, we know based on atomic physics and how galaxies work and these sorts of things, there's supposed to be these nice emission features at these wavelengths. But then with our telescope, we measure and we find these exact emission features at a redder wavelength. And so all we really do is we're measuring this distance or this change in the expected wavelength, the expected location of an emission or absorption line or some feature in the spectrum to where we measure it, I guess, when it hits our telescope, hits our detectors, runs through the very nicely coded PFS pipeline. And then we can finally measure that change and get a redshift. And based on that redshift, we can determine how far away something is. And so if we know how far away something is, we know, okay, it's close to another galaxy, it's close to a whole collection of galaxies, all these sorts of things, and allows us to really answer and fully constrain a 3D picture of where a galaxy is located. I know that's a lot. So why is ʻŌnohiʻula PFS amazing for this? I think we've touched on this a couple times. We can do this for 2,400 different things at one time. That's a lot of different things. We can cover large areas of the sky, like Brian kindly reminded me. These protostructures are very, very large, and so having a large area on the sky, we can really capture the full extent of these structures rather than zooming in on one particular part. And then it's something else that has been mentioned a couple of times is there's a really good wavelength coverage where we're covering from a little bit bluer than what we can see to redder than what we can see, and we're getting a really long baseline, potentially see all these different features in a galaxy spectrum.
So the superstructures that we target, the biggest of them, are tens of arc minutes on the sky, right? Roughly. Right. So maybe half a degree or so. Yeah. There's effectively no instrument on the planet nor above the planet that can cover. There's one on Keck that is like kind of oblong, but that can cover the full extent of these structures in a single pass. And so it used to be that we did many passes to get the single structure, but here we're getting multiple structures, superstructures in a single pass. Yeah. So we've inverted the problem towards much higher efficiency.
Yeah, which is very exciting.
I mean, not currently,
but well, that's the main goal. Yeah, I think that's maybe one of my last slides. I have a few pictures that Brian and I actually were up at the telescope yesterday. Here's a few fun pictures. If you want to understand maybe with people, this is kind of the size and scope of how big the Subaru telescope is. PFS, or part of the instrument, is up here, kind of in this spot called Prime Focus. And so the light will come down, hit this main mirror here, bounce back up to kind of the Prime Focus, and then do a bunch of other optical fun things that maybe Moritani-san will talk about in the future. I have two extra bonus slides about AGN stuff, but I know we're at 8:11.
Oh, it's okay. Yeah. Yeah. So is PFS in this picture?
So the part that feeds, so the spectrograph itself is actually in a room, I think in this picture on the left side, because that's the near infrared side. So it's to the left over here, in a nice sealed environment controlled room where humidity and light and other things won't mess with how all the optics within the instrument are working. And so the light will get fed through some fibers from up here.
Yeah, so that's the PFI that Kumiko mentioned.
Yeah, I forget that.
Prime Focus Interface?
Yeah.
Instrument. Okay. All right.
Yeah.
And so that controls all the fibers, and then it sends the fibers to the spectrographs in the NASMET deck, the IR portion of the NASMET deck.
Yeah. Cool. I have two bonus AGN slides. I will briefly go through these.
All right, Finn, this is Roy. Can I just do a quick interrupt since we were talking about PFS and power? For those online joining us, this instrument is a good example of how ground-based telescopes can evolve over time to take advantage of new technologies. And we often hear, like, why don't you just do everything in space? When we have new technologies, we can't just go up to like James Webb Space Telescope, which is an extremely far away, and attach new technology to it. It's actually out there with technology that's 10 or 20 years old when it was first developed. So on the ground, we develop new technologies and we can improve the power of our telescopes. And in this case, we've gone from telescopes that could do like 100 objects or 200 objects at once to 2,400. So suddenly we've made our telescope 20 times more efficient with this new tool than it used to be. And actually, if you multiply it by the fact that it's optical and infrared, it's 40 times more efficient. So imagine if you took your car from getting 20 miles per gallon to 800 miles per gallon, you'd be pretty happy, especially today. So we're able to do this with our telescopes as we develop new technologies. And that's a really powerful thing for these ground-based telescopes, and why they have very long lifetimes of 50 years, sometimes 100 years, depending on their abilities, their capabilities, and their design.
What's the overall weight of PFS too? Like if you added up all the spectrographs and everything, roughly.
PFA is three tons.
PFI itself is about a half ton.
Half ton.
The lens is 3 tons.
Okay.
This spots. Yeah.
So the lens is 3 tons. Okay. And then all the spectrographs, how heavy are those? Plus I guess you need all the electronic modules too.
Yes. So then one spectrograph is 1 ton.
1 ton.
Yeah.
Okay. So over 5 tons altogether.
No, but spectrograph is on the dome.
Right.
Telescope.
It's not on the telescope, but just the idea of sending all of that weight into space, thinking about doing this in space, this would be absolutely prohibitive. You couldn't develop this type of technology, or it would cost way too much money to do it. Yeah. So this is another way that ground-based telescopes win, because we can just stick it on the side of the structure and everything's fine.
Yes, which is exciting. Sweet. I have 2 bonus AGN slides. I'm going to go not quickly, but I unfortunately probably don't have the time to go to all the details. If you wanted to look at a spectra, you can get many other things besides the redshift. One, I guess, case for maybe 100 or 200 objects we were planning on observing tonight is we were going to take a spectrum of things called active galactic nuclei, which I think I mentioned earlier. Essentially, you've got a galaxy where the black hole in the center of it is actively accreting material, or so there's gas and dust that is, I guess, flowing into that system. And so there's lots of ways you can study that process. And one way that I'm working with one of my collaborators, Dave Sanders, on is looking at particularly this emission feature here and this emission feature here. So the magnesium-2 line and the H-beta line. And essentially, if you
measure, just a quick, so you're plotting brightness here on the y-axis, and it's versus wavelength and nanometers. And this is a prime focus spectrograph.
Yeah, this is a spectra that was taken in 25A actually.
Mm-hmm. Right. Okay. So for basically the first night of
one of the first nights of observations spectra that we have here. I think this is maybe one of the older reductions, but
okay.
Yeah. So we've got brightness.
Sorry, one other thing is that because it's so efficient, you actually can't fill up all the fibers, or it requires a concert of different science goals.
Yeah.
Right. So you have your main science case that you explained beautifully earlier. And then you have several other collaborators that are sending targets. Yeah. Even in the first run of BFS, we had very, very distant galaxies that were included as part of it. You have more close by galaxies that are hosting accreting black holes. We have older galaxies that we're looking at. We have all sorts of complicated science goals. So it's all wrapped up into these, single 2,000 objects at a time. Of which 1,500 or so are the objects that you're looking for, and then there's this smattering of others.
There's a few other objects, 100 other objects, where we can try to answer all these other science questions aside from those two main ones that I was talking about. Yeah. And so I guess looking at this brightness versus wavelength, I think one thing that people are particularly curious is how, broad or wide these lines are. And essentially, I won't get maybe into all of the AGN physics, but essentially, you can measure, this is kind of a complex plot, but this is an inset down here of the two lines I was talking about, the H-beta line here, magnesium-2 line here, where again, it's a brightness versus wavelength. And if you can measure how broad or how wide these lines are, you can do a little bit of math and determine how massive the black hole at the center of this galaxy is. And so, for example, for this source, I think the black hole mass is probably 10 to the 8 point something. And so that's 10 to the 8 solar masses of material, log solar masses of material. So take the mass of the sun, very massive thing, times 10 to the 8. Very, very, very massive, 100 million times more massive than the sun, sitting at the center of this galaxy that's accreting material in such a way that we can try to measure and back out how much mass is actually there. And that'll be probably the brief AGN interlude for now.
I thought black holes didn't emit light, Finn.
Well, okay, it's you're not getting the light from the black hole. You're getting the light from the accretion disk of material around the black hole.
Okay.
And so that is rotating very quickly, and maybe another time we can get into what causes different emission lines to broaden, but perhaps not today.
Okay, but the rotational velocity is in some way correlated with the mass, and that's the idea. Yeah. Great,
cool.
Thank you, Finn.
There may be questions in the chat. Oh, thank you, Randy.
Yes.
Yeah, so Bonnie, Yuki or Akira, this might be a great question for you. So, or actually any of the Subaru support astronomers that are in the room. So Bonnie asks, what specific calibration stars or sky exposures are needed to compensate for atmospheric dispersion, instrumental drift during long exposures? So we do, 15-minute exposures.
Then in one field, actually not only that science target, we secured some fiber, allocate some fiber to sky object, also flux standard star. So which was used to calibrate the sky brightness spectra, also calibrate the flux. Then for atmospheric dispersion, we don't have any specific star, but the wide field collector have some optics to compensate the atmospheric dispersion. So we just rely on that.
Right. So it corrects atmospheric dispersion for all of the fibers simultaneously, makes some sort of bulk correction. Because there's a huge wavelength baseline, that's extremely important, right? Because the blue light near the atmospheric cutoff is going to bend very differently, disperse very differently than the near infrared light.
Then we need to configure the position fiber every 30 minutes, considering the drift.
Right. So yeah, we do, normally we do, well, it depends, 2 15-minute observations or 4 7.5-minute observations. Then there's a reconfiguration of all the fibers using the cobras, and then relative to fiducial fibers, right? And then we start integrating again. And when everything is working perfectly, which it always has been when we've been here, that process is seamless. So the reconfiguration happens within a minute or two, and then we just start observing again as if nothing happened. But so it's roughly like a couple hundred sky fibers and then maybe 50 standard stars or something like that in that range.
40 to 50 standards and the maximum 200 to 400 sky fibers.
Right. Okay. Yeah. So there's roughly 1,800 or 1,900 fibers left over for science in the end. And then the rest is a web of calibrators that allow you to reduce the data. Because of course, so there's a fiber spectrograph, it's not a slit spectrograph. So you get the sky plus the object in an observation. It's just a light bucket that gets everything. And so you can't do the sky subtraction. The sky is much brighter than the objects.
Something might be helpful too.
Perfect, yeah.
Show,
And so you need fibers that have no object and then interpolate over all of these fibers to then determine the sky subtraction at a given location.
Yeah.
Ben, do you want to run through what this is?
Yeah, so yeah, this is just showing, I think this is one of the, I guess, this should be one of the potential, I guess, fiber design setups we were going to try to expose during, or I guess observe during this run. And so you can see.
This one from tonight? Or?
This should be, I just grabbed one of the recent ones I'd opened, so hopefully it's one of the ones for tonight.
Mm-hmm.
But you can see each of these dots is a different fiber, and the kind of pink ones, if they're showing up well in Zoom, is the kind of science fiber. So those are targets that we've tried to set as, I guess, the astronomers. And then you've got the sky and flux standard, which I guess Moritani-san and Brian were just talking about. So yeah, trying to correct and do all the different things. And those are in the green and the blue. There are some fibers that are currently broken. Those are the X's. And then you've got guide stars out here in the purple that kind of help keep the whole field of view kind of in the right spot.
Right. Yeah, so you guys have 6, is it right? Guide chips. And so then you pick out Gaia stars and you then track based on the location of the Gaia stars. Yeah, so there's, in addition to all of these optics, there's the flanking optics, which allow you to do the bulk tracking, right? To precision of 0.1 arc seconds or something like that. Yeah.
So yeah, just trying to visualize kind of what we were talking about, getting all the fibers put into the right spots as best as we can to maximize, I guess, science output on the observations.
But to be clear, we basically do nothing.
Well, I submit a target list and
Subaru the people that actually know what they're doing do it.
Kindly put something together for me, and then I get to ask them to change it slightly.
So there's another question, and Yuki, I think this is perfect for you to maybe talk about the background of PFS and then some of the challenges that you've run into. So the question is, what are some of the biggest technical challenges in operating an instrument like this? And I'm sure there are many that you guys have already solved and still many to solve. So maybe if you want to give a overview of PFS and Yuki, might I ask you to maybe come over here or happy to make space.
Shuffle around.
Let me try Wi-Fi.
Oh, shall we take over here?
That's this one. I think that's fine. I think here is fine. If you're okay. Yeah. Sorry.
I just don't.
So I hope that you can hear. Can you hear my voice?
Yes, we can hear your voice very well. Thank you.
Yeah, mine.
Yep, perfect.
Something I have to show the slideshow slide. Okay, so yeah, so again, my name is Yuki Moritani. So I'd like to introduce briefly about ʻŌnohiʻula PFS, the instrument overview and integration. Then, so as we talked about, the ʻŌnohiʻula PFS is the fibers field spectrograph. Then it's the newest and very powerful instrument at the Subaru telescope. The science operation actually started just 1 year ago. And this is the snapshot of first light, and you are there.
Yeah. We were comparing what we're wearing today. It's pretty much the same. As most scientists, we never change our clothes.
Actually, since the first light, more than 90 nights were allocated PFS. So we carried out 90 nights. Then we hopefully have the 100th anniversary in this run. So then this is the right figure showing the how the PFS instruments are distributed on the telescope. So the PFS is a big and complicated instrument. Then on top of the telescope,
yeah.
Okay. So on the top of telescope, we have the instrument called Prime Focus instrument. Then here we get the target, light from target using the fibers. Then also in the dome building on fourth floor, we have the dedicated clean room, where the temperature is controlled to 5 degrees Celsius. Then here we have the force spectrograph. Then in between, to connect the light, to deliver the light from the top of instrument prime focus to the spectrograph room, we have the 55-meter fiber cable routed along the telescope, then going up to the dome. Then we have another instrument at the Cassegrain focus to measure the fiber position. So it's called the metrology camera system. Using this one is look at the telescope, then on the focal plane, they measure the fiber position. Then this figure really show how PFS takes the science data. So the PFS is very strong. Then we have the 3 main points of the strongness. Then one is the wide field. So this figure, I think Kumiko showed before. This photo is M31 Andromeda galaxy. Then it was taken by hypersprint cam in one single shot. Then we share the big lens with HSC. The field of view is a little bit smaller than HSC, but still we have about 7 times as large as full moon field. So we have still very wide field. Then second point, high multiplicity. So in this figure, you show many dots, many marks. Then each mark indicates the fibers. So we have 2,400 fibers here. Then different colors show the fiber to be connected to the different spectrograph. So we have 4 spectrograph. Then each spectrograph cover the entire field sparsely. Then this fiber actually is connected to motor, which calls Cobra. So this is one aspect fiber positional module. Then this has actually 57 fiber is assembled to one module. Then we have 42. Then maybe you can calculate how many fiber are there. Then each fiber is connected to this kind of motor. Then this is the 2 rotated axial motor. So theta and phi. Then it looks like your arm. So theta looks like your shoulder. So you can rotate the shoulder. And the phi looks like the elbow. So you can open and close the elbow. So then fiber. Then on the top of the hand, we have the fiber. So you can move the fiber in the patrol region. Then each patrol region actually overlap with each other. So in the field of view, anywhere we can allocate the fiber anywhere unless it collides. Then this is Yeah. So this, how can I? This is a movie to fiber configuration. So quite nicely. So each motor moves to, at the time. So then using the metrology camera, measure the position, then iterate, then like at this. So we usually do 8 iteration. Then it takes 2 or 3 minutes. Then this is just a speed up. So like this, you can configure the fiber very quickly. Then this is another shot about the instrument. So again, this is a telescope. Then here we have the metrology camera. Then top of that, we have the prime focus instrument. So the metrology camera has a large format CMOS camera. So it can take 2,400 fiber spots in one single shot, then calculate the position. So from looking up, so the fiber, for example, looks like this. This is actually pinhole mask when we test the metrology camera, but the image looks like this. Then if you can see this screen. Or
no, we can't share it, unfortunately. Our gears isn't working very well, but yeah.
Okay. So then again, I say that multiplicity. Then also sorry, I say the third point is wide wavelength coverage. So then by allocating the fiber, we can get the spectra, 2,400 spectra. Then the spectral range is almost 380 nanometer to 1,600 nanometer. So almost a blue to near infrared. Then we can take this wide wavelengths at a single shot. So this is the spectrograph. So this is the inside the spectrograph. We have 4 module is inside it. Then just feeding the size, human looks like this. So it's kind of very big room. Then also this is another shot about the spectrograph in the middle of integration. So the bench is about 24 meter and about 2 meters. So maybe around the size of the double bed or something. So on it, we have 3 cameras. Each module has 3 cameras, blue, red, and near infrared actually here. Then we have dichroic mirror. Then using 2 dichroic mirrors, we can take the wide wavelength spectra in one shot. So actually, typical exposure time is 15 minutes. Then in one night, a PFS can obtain about 40,000 spectra per night. So I think you feel it's enormous. I hope. So then TFS is an internal collaboration. So the Kabula University Tokyo led the project in collaboration with NAOJ. Then the collaboration is from the 7 countries and more than 20 institutes from US, Europe, and East Asia. Then if in terms of instrument overview, so instrument travels a lot actually. So here is a destination, the Subaru telescope. So for example, spectrograph was integrated into France. So then
that was at Lam.
This is Lam. Yes,
okay.
Lam. Yeah. Then he actually from Lam.
I spent 4 years at Lam too. Yeah.
Then to integrate the Lam, the camera is actually shipped from the East Coast, then fiber from the Brazil. And also Japan had sent some parts too. So they integrate in France, then come to Subaru. Then Prime Focus instrument and metrology camera is assembled in Taiwan. Then to assemble the spectrograph, PFI So fiber is first made in Brazil, then go to California, then go to Taiwan, then back to Subaru. So previous experience many travel. So then we started integration in 2018. So starting from metrology camera system. Then actually the last one come here, the near-infrared camera. So then we did it takes 6 years and 4 months to deliver all instruments from world to Subaru. Then actually that's a snapshot. So we transport the 14 transportation in total. So Hiro base here to Subaru is about 70 kilometers. They also some instrument delivered to Kona, and we transport from Kona to Subaru at about 100 kilometers. So then thanks to very nice job, they grew even though very bad weather. We managed to get the instrument, then we can transport, integrate the instrument. Then this is a snapshot of integration of Subaru. So for example, to route the 15.5-meter fiber cable, more than 10 they grew and instruments work together to route the fiber like this. They are route on the spider, then using the radar. Then it takes 2 or 3 days. So then also this is the movie of the integration of spectrograph. So this video showed 1 or 2 weeks work in 1 minute. So this happened at the above the Mauna Kea, on the top of Mauna Kea, 44,200 meter altitude. So then module delivered as a module, they integrate like kind of this. So then we did this one for 4 times because we have 4 spectrograph, but team works very nicely, so we managed to put it together. So yeah, now
This was really done
getting
in
there.
2 to 3 days.
Hmm?
This was really done in 2 to 3 days.
Yeah, main part is 2 or 3, but to prepare is about 3 days. So in total, it takes 1 week or in the
Still very fast.
So yeah, then after it, we have some engine grant to make sure the instrument performance. So like today, observer in Hiro, and also sometimes we have Mitaka. Then we used to observe the TFS at the summit. Actually, we need to troubleshoot with something happen. So currently, we observe that we had observation only the Hiro, but used to at the summit. Then yeah, this is one of the important things to survive the turbulence. Then yeah, this is just brief introduction. So then I think that's all from my slide. So then stop the share.
Thank you, Yuki.
Yeah.
I'm wondering if you could mention like what the most difficult parts of the process have been, like from the beginning to the point where you started doing the commissioning, and then since the commissioning, if everything's gone smoothly or if you've run into challenge. There's always challenges, right?
Very challenging.
Yeah.
So I think that during the commissioning, actually, I didn't imagine it took such a long. I didn't imagine it takes 2 or 3 years actually. So at the beginning, we struggled to operate the instrument very stable. We had some issue in the electronics of PFI, and we had to cancel observation due to instrument. So getting the instrument more stable is one challenging, even though it tested before shipping. So after shipping and also integrating all together is a kind of challenging.
Yeah. But that's not enough. I mean, when we commission a Gemini, it's also roughly about that amount of time. And I mean, the number of moving parts in this system are unbelievable to get it working smoothly. I mean, even commissioning a single integral field unit at Gemini takes a year and a half. I can't imagine this level of complexity.
They also currently we started the science operation. Then I mean we have many spectra ever than before. Then by analyzing the many data, we know we learn the new thing how to optimize instrument and how we need to modify the instrument. Then getting new things is really nice, but also I think it's challenging. So and also it's nice, but
and one thing that's that you didn't mention is that Subaru provides data reduction processes as well. So you take the raw data and go all the way to effectively science-ready data. So there's a whole division of people that work on the data reduction processes as well. And this is something that's becoming more common at large observatories. At Gemini, we also provide data reduction support. But that for an instrument of this level of complexity, that is incredibly difficult to get right. And then you have annoying people like us that say like, hey, by the way, the noise properties aren't exactly right and all this kind of stuff. And so it's always an iterative process. Yeah. Well, thank you very much for that. It actually leads into another question that we just got, which is how do you go, like, how long does it take you to go from raw data to publication? And can you describe a bit the process, like specifically for PFS? I know we don't have a publication yet, but
Working on it.
working on it.
At some point, yeah.
But how is that experience, especially with a new instrument where I mean the discovery space is completely wide open, and so you never kind of know what you're going to find.
It's definitely been iterative. I think it's a time scale of, you take the observations, they need to be, stored and downloaded and put through a whole pipeline of reduction, and that takes time. It's not if we were to take observations tonight, it's not tomorrow morning. I have a nice spectra to look at and maybe try to make measurements that I was talking about earlier, like measure redshift or measure width of a line or something. And so that's a process that'll take weeks to, I guess at the end of the time, get that on the very kindly provided platform that I can be able to access the data on. So that's weeks to months of time, and then it's weeks to months of me playing around and understanding and trying to learn, okay, what kind of things and what kind of measurements am I able to make with this data? What does the noise look like? Is the sky background messing with maybe adding extra features into the spectrum that I don't want? These sorts of things. So that takes months and months. And then maybe there's something you have to go back and recheck, and the data gets reprocessed, and that's another month or two. And so I would say between reducing the data, analyzing the data, and then finally probably making some sort of sense out of a final publication will probably take a year and a half or so at least, right?
At a minimum, yeah. So a lot of astronomers, if they're really motivated, maybe even a couple months they can do it. But data this immense, and for the type of, because even after we make the measurements, then we have to feed that into our cosmic cartography pipelines and then our measurements for physical properties, and then we have to combine all that for an analysis. And so even when you're sure that the data properties are right and everything is science ready, it still takes years. Honestly. This is why PhDs are
years
measured in billions of years.
Brian, it's Roy. I wanted to add that, of course, this depends on your project. So not everything is like that.
Yep.
We're doing surveys like a census, which takes a long time. But we've been on projects related to this, or even different ones that we've done throughout our career, where you discover an interesting and exciting object. You take data in a night. It's processed using existing pipelines from a camera that's been around for 20 years. And it's super cool and hot, and you get it into the journal in like timescales of weeks, and in some cases even days. So it can go very quickly. Like the discovery of Oumuamua, there were papers about that submitted within days.
Yeah, 3i Atlas as well.
Yeah.
Supernova folks work very fast as well, usually too.
Yeah, it's good. So we have one other talk that we wanted to get to before we close the session.
It's from
So can we go? Yeah.
Hi, my supervisor, one of the key person to develop ʻŌnohiʻula PFS is Professor Naoki Tamura, and he is on Zoom. Tamura-san, do you hear me?
Okay, thank you. Unfortunately, the weather is not cooperative, but hopefully the people are enjoying watching what scientists are doing, and their talks about physics, astronomy, and instrumentation. So that's great. Now I'm just quickly trying to add a little bit of another story behind the scenes, which is about the name of the instrument. So the name, the instrument has been called Prime Focus Spectrograph since beginning a few 15 years ago. Basically because it is a spectrometer exploiting the prime focus of the Subaru telescope. But there was a floating idea for quite some time among multiple people in the PFS collaboration to update the name. And one possibility was to make the instrument sound more domestic in Hawaii, because it is being installed and operated in Hawaii on the Subaru telescope. And in fact, there is a project ongoing called Akueho Inoa at Imiro Astronomy Center of Hawaii, which gives Hawaiian names to astronomical objects, for example. So we contacted Dr. Devin Chu, who is the resident astronomer of Imiroa, and then Devin mediated us between us and one key person in Hilo, working on Hawaiian language and Hawaiian studies. That is Professor Larry Kimura at the University of Hawaii Hilo branch. Kumiko-san, could you go to the next slide?
Yes. Oh. Yeah. Okay. Go ahead.
Thank you. Yeah, thank you very much. The name he gave us, or gave this instrument, is ʻŌnohiʻula. So this is a connected word of two words. ʻŌnohi, which means the vision, focal plane, our eyes, and so on. And ʻula means, I think, the sacred red originally, but actually, apparently, it also means some origins of us. Actually, we didn't directly meet Larry Kimura until recently. Devin Chu, we talked about our instrument and what we are trying to do with PFS to Devin Chu. And then Devin actually told Larry, because Devin is a professional astronomer, about how PFS works and what the science missions we are going to aim at. And then we met in person in the naming ceremony in November last year in the Subaru Hilo-based facility. And then we, of course, re-explained how the instrument works and what the science vision from PFS. But then Larry told us that he actually reasonably immediately came to this name once he understood how this instrument works and the scientific goal of this instrument. Because in a large picture, for example, the long-term survey that is ongoing with PFS, the collected data should be used to better understand the origin of dark matter, the origin of dark energy, the origin of the variety of the galaxy populations across different epochs, and so on. That is really the origin of many things. And the PFS is kind of compound eye for that. Even after Larry Kimura heard from us about the explanations of the instrument and science goals, he just reconfirmed that this name is perfect fit to this instrument. So yeah, I think that's all from myself. Thanks, Kumiko-san, and thanks everyone for giving me this opportunity.
Thank you, Tamura-san. Could you introduce Murayama-san a little bit?
Yeah, sorry. The guy on the lower left in the photo, talking to Larry Kimura, he's Professor Hitoshi Murayama. He is the PI of this entire PFS collaboration, so he is really the leader of this entire collaboration. He is based at University of Berkeley, California, Berkeley. But when he really launched this collaboration, he was the director of Kabri IPMU at the University of Tokyo. And he actually recruited me to join the development of this PFS instrument. And then I was working for Kabri IPMU for 11 years. And then once the instrument was nearly built and assembled, I moved to NAOJ. So this is a bit of a summary of Hitoshi and myself.
Thank you so much, Tamura-san. And if you're out of Hawaii, you may not know about the Hawaiian naming project, but you may know the Oumuamua, the interstellar object, or Povehi, its black hole shadow of M87. They are named by Ahuahe Inoa group. And also, you may know Mauna Kea Observatory's website. If you want to know about ʻŌnohiʻula, more details, please visit maunakeaobservatories.org and click stories. And we are fortunate to have a very nice article behind the scenes of ʻŌnohiʻula. So please visit Mauna Kea Observatory's website. Thank you.
Thank you both. Yeah, thanks for this background. So I think we're going to switch back to the observations really quickly, or the lack of observations. So as people can see, there's 8 screens here that we use to monitor the instrument and the weather and a variety of other things. And Joel has all of these screens up on his computer. And so I was hoping, Joel, if you could show S6, which is the weather screen.
Yep. I've been trying to pull it up for the past like 20 minutes, and it's just giving me like a 3-dot screen. I mean,
Oh, sorry. I thought you had it running already. Okay.
Oh, well, no, I clicked on I connected, right? And I clicked all the screens, and it's just giving me the dots.
Okay. Okay. So maybe
Screens or all the screens?
are all the screens giving you dots?
Every screen.
Oh, okay. I don't know how good this camera is.
I can bring my laptop.
Oh
over.
yeah, if you could.
Sorry about that. Yeah, I know it's just a few tech issues.
No, that's okay. Jamika, can you highlight? Can you pin my screen?
Gotcha.
There we go. Okay. Yeah, high tech.
Yes.
Woo!
Yeah. Okay, that's not the nicest view, but you can see this is our monitoring screen. So we have all the telescope status here, like where we are pointed, and we have here all the environmental conditions. So here you can see this is our humidity. So it's currently red. We're in a humidity of around 80 to 90% right now outside, and we have here the temperature. It's around 0 degrees, so around freezing. We also have wind speed, inside humidity, dew point, everything here that we need to know for our environment and the telescope.
Yep. And there's a lot of red there.
There's a lot of red, which is not good, yeah. So you can't see anything here right now, but if we were observing, these are our 6 outer guide cameras that we were talking about before. So you could see all our guide stars in here, which the telescope is guiding on. And here are our guide errors, so showing like how good our guiding is. Then the next screen, here's one image we wanted to share before but couldn't. So this is a very nice image. This is an image of our, if we could see that, the meteorological camera. It's the image the meteorological camera took of all the fibers, which are illuminated here. So you can see all our around 2,400 fibers in that image. We also got some other, oh, no, sorry. Up here. Sorry about that. We also have some other screens here we can monitor. So we have some alarms popping up here currently saying high humidity.
Thanks, alarm.
Yeah, thank you, we know. Then down on the other screen, that's our Gen 2 interface. So this is where we actually execute our observations. So we can slew the telescope to a field and then get the start the exposure and start exposing with PFS. Then over here, we just have some more cameras pulled up. This is the Gemini cameras that Brian showed us previously. Down here is our also some monitoring. And so we can actually pull up all the targets and we will know on our nice all-sky camera where our targets are distributed. So where we are going to point the telescope. And then this screen is our PFS interface. It's basically showing all our instrument status. If we need to interact with the instrument, we can use this screen.
Are these biases or FUDS? Or...
what do we have here right now?
This is the halogen spectra of the engineering fiber.
Okay.
Yeah.
Okay.
Yeah, we took some engineering data before to test the instrument. So this is just one of the plots, the recent exposures we took here. And
so these are the only photons we're getting today, seems like.
Only from the calibration lab, unfortunately, yeah. And this is our last screen we have here that just shows a bunch of different things, shows us our focus, how good we are focused. You can't see anything here right now, but you would see also our guide error here and how good our the convergence of our fibers are. So right now it's pretty good. So you would see how well the fibers move to their assigned targets, which is very important for getting good science data. Thank you so much, Brian.
Yeah, thanks, Vera. Yeah, we were able to high-tech this. See all the screens. Okay. So we're running right on the hour now. I just wanted to pass back to Kumiko if you wanted to talk about the last part. Yeah.
Oh, okay. Thank you so much. Okay. So after my short talk, we finished, right?
Yeah. We'll probably call it. Yeah. Unfortunately, it looks like the humidity is still trending, and there was a sucker pull, but
like,
yeah. that's the sucker movement.
yeah, it was excited.
Okay, I want to make some announcement from Subaru telescope. I want to share the not this one side, sorry. Excuse me. Okay. So let me introduce our website, and Subaru telescope have some very fun digital content you can enjoy anytime, anywhere. This is our website, subarutelescope.org, and you can scroll down a presenter reading topics or science results. And also we have many beautiful pictures taken by Subaru telescope or taken on Mauna Kea. Click Subaru Gallery, and please scroll down, and we have some fun content like Subaru virtual tour. You can explore inside of the Subaru telescope anytime, anywhere. And also we have, in collaboration with Asahi Shimbun, Japanese newspaper company, we NAOJ collaborates to set up the Mauna Kea starlight camera. Please go to YouTube, Asahi Astro Live, organized by Asahi Shimbun, newspaper company, and please click live. So the YouTube account is Astro Asahi, and click live. You see many live stream, not only from Mauna Kea, but also some places in Japan or even in Chile. And we have 2 star cam, live cam, from Subaru Asahi star cam toward north, toward the east. And number 2, CFHT Asahi star cam toward west. So this one is the first live cam, Subaru star cam. Oh, now we see stars from Mauna Kea. So you see two Keck telescopes. And also when we go back, here CFHT Asahi star cam. Oh, we see Subaru,
Subaru.
the Makali, yeah.
Mhm.
The Pleiades over here. And we see that. So the CFH camera is toward the west. So we see Subaru, Keck, IRTF. And we see another Subaru, the Makali or the Pleiades. Oh, now we see stars on Mauna Kea. So please enjoy our fun digital content anytime, anywhere. Thank you so much, Brian.
And so does that mean we open up now that we see the stars? Oh, there's other conditions besides stars. Ah, I get it. Okay, not just clouds. Okay.
Okay, I stop sharing.
Okay.
Thank you.
Okay, well, I think this session has come to a close. Unfortunately, it doesn't look like we're going to open up during this session. We do have another session tentatively planned for Friday. There is a storm coming. This is the beginnings of the storm. And so we'll see if that session goes ahead as planned, but that will also be with all of us and with PFS as well, if it happens. So hopefully storm is not as bad as predicted, and we can open up later tonight. We can dream anyways, and then maybe later in the run. But thank you so much to everybody in here and all the participants for joining us. This was a lot of fun, even if we were closed the whole entire time. And yeah, there's upcoming sessions on Gemini on March 20th, although I think that's a dedicated session, right, Jamika?
Yes, that's right. That's right. That's a dedicated session for students who are part of the European Union's PICO project.
Right. Okay. Right. So I'll be observing on Gemini for that one. But we do sessions with Gemini, either north or south, every month, effectively. If we don't have our session on Friday, we will certainly be back at Subaru, and we'll certainly do another session here. And there's also another instrument is being featured now at Subaru's C3VO and Shot of the Scientist session. So there's plenty of possibilities for engagement for people that are interested. So yeah, thank you, everybody. Thank you, Jamika, for emceeing everything. And aloha, ahuiho. See you next time.
Yes.